forward propagation, or how to compute the output h of x. Forward propagation. Okay, now the reason we have to discuss how to compute the output, okay, because as you can see, this visual representation is sort of, nice, it's convenient, it lets us know what's going on, cascaded perceptrons, okay, but we don't have a very nice convenient formula for the function h of x, okay, like we did for the linear perceptron. We don't have a convenient formula, okay. In fact, I mean, we could construct one, okay, but it would be a very cumbersome, almost useless formula to look at, okay. Instead, okay, we can get a very nice, convenient general algorithm, okay, that takes as input the set of weight matrices, okay. So we will call the set of weight matrices W. Okay, so the set of weight matrices, take the set of weight matrices W, okay, and the input, and then this algorithm just runs and produces the output. Okay. So it's an algorithmically specified final hypothesis. Although if we wanted to, for a fixed collection of weights and a fixed input feature, we could sit down and write the explicit function, but it's not much practically useful. It's not really useful. Okay. Now, I'll just mention that, by looking at these weight matrices, so this weight matrix has embedded in it the dimension of this layer and the dimension of this layer. This weight matrix has embedded in it the dimension of this layer and this layer. This weight matrix has embedded in it the dimension of this layer. So if you tell me what the weight matrices are, by just looking at their dimensions, I can reconstruct the network. So implicitly, by specifying the weight matrices, and that's all you need to specify, you have not only specified the architecture of the neural network, but you have also specified what weights go on each edge. And that's typically how we specify the neural network. We say, just give me the weight matrices. You've told me everything I need. Okay. So now, let's focus on, the input to node Li. So the input to node Li is, the ith column of, it's a perceptron, okay, that's being computed with respect to the previous layer's output. Okay, and what are the weights of the perceptron? It's the ith column of L. Okay, so the input to the input SLI is just the perceptron computed using the ith column of the weight matrix and the previous layer's output. So it's just the ith column. So the weight matrix is the ith column of the weights are the ith column of the weight matrix transpose XL minus 1 applied to the output of the previous layer. So this is just the linear signal. So this is the linear signal. Okay, and this here are the weights of perceptron computed by node Li. Okay. So, you can think of this as, a row. So SLI is this transpose, which is a row times the previous output. Okay, so let's now look at the vector SL. Okay, is SL1, SL2, all the way to SL. What's the dimension of the output? DL. Okay, so let's look at the weight, the entire input to this layer. Okay, the entire input to this layer is just, the weight matrix WL1 transpose, okay, which is now a row, times XL minus 1. WL2 transpose times XL minus 1. WL3 transpose times XL minus 1, and so on up to WLDL transpose times XL minus 1. So this is just the matrix WL transpose. So the signal SL, so summary, okay, the signal SL is equal to WL transpose XL minus 1. Okay, so we can compute that entire vector signal into the layer L with just one matrix multiplication. So the matrix multiplication of the weights WL, okay, transpose, times the vector output from layer L minus 1. This matrix representation is very useful when we come to implement huge networks, okay, in practice, okay, because we can specialize hardware and architectures and algorithms that can become specialized for computing this matrix vector product. Okay, and you can distribute it on GPUs and so on and so forth. In fact, GPUs have become very good at computing matrix vector products. Okay, so if you want to speed up, the computation of this signal, you just speed up the computation of a matrix vector product. Okay, so let me erase, what led up to the signal. Okay, and now that we have the signal, we can compute the output. XL is just, and I'll heuristically write it as theta because they're all using the same transform. So I apply this transform theta, tan H, I apply this transform theta to the signal, okay, and add the augmented one. 1 theta of SL. Okay, so mathematically, that's what's going on in layer L. Okay, now let's put this together. Let's cascade and get the final output H of X. And that's the forward propagation algorithm. So the algorithm, okay, so forward propagation algorithm in step 1 is to initialize. So let me just tell you what we are computing. Okay. Given the weights, WL, okay, W1, 1, W2, and so on, up to WL. So you're given the weights, okay, and you're given an input. So these are the weights, the architecture and the weights of the network. So the weights, okay, and the input, X, which is 1, X1, X2, up to XD. Let me call it little x. Okay, so this is the input. Okay, compute H of X. Okay, and it's a straightforward, very simple dynamic programming algorithm. You compute the output of the 0th layer. So step 1, initialize. Okay, compute the output of the 0th layer. So X0 is just initialized to X, the input features. Okay, now propagate the output of layer 0 to the output of layer 1, then to the output of layer 2, 3, 4, and finally to the output of layer L, and then you're done. Okay, so this is initialize. Step 2, propagate. Propagate. Okay, so assume, okay, so in some sense, compute, so set, the layer that you're working on, L equals to 0. So you've initialized, layer 0. Okay, now propagate. Set L equals to L plus 1. So we're going to now compute the output of the next layer. We started with L equals 0. Okay, and we compute first the input to that layer. Okay, SL is equal to WL. We have WL, it's one of the inputs. Transpose X L minus 1. So when L equals 1, we use X0, which we have computed. And once we have computed S1, okay, we need X0, which we have. And then we compute XL. The output is just, 1 theta of SL. Okay. So you propagate, okay, until you have X big L, okay, and X big L, H of X is just X big L. Okay, so this is the 0th, this is X big L, so this is the 0th component, the augmented one. Okay, so there's the augmented one, and then there's the output X big L, 1 of the first non-trivial node, not the augmented node, the first non-trivial node. Okay, so you just initialize and propagate. Okay, we could say, you start at L equals 0. Now for L equals 1 to big L, okay, you output in this way. So L equals. So effectively what we're doing is for L equals 1 up to big L. Okay, and then when we have XL, output XL, the first output. And, you know, it's very easy to update this if you want more than one output. Okay. So let's say you're doing a massive vision problem and you have 25 classes, apple, orange, dog, cat, and so on. So then you'll have 25 outputs and you can view the output H for each of these outputs as the probability that it is that class. Okay, I'm not going to get into those details. We're going to focus on the basics. Okay, so that's forward propagation, or how do we compute h of x? Okay. At a high level, what's going on? Okay, so let's just show you what's going on in forward propagation at a very high level. So at a high level, you initialize your neural network with x, okay, and then the first layer weights, well, x, which is x0, which is initialized to the layer 0 outputs, and then your first layer weights come and give you the signal that's going into the first layer, and then you transform and you get the output of the first layer, okay, and then you apply the weights in the second layer, okay, and you get the signal into the second layer, and then you transform and you get the output of the second layer, okay, and dot dot dot, eventually you get the input to the Lth layer, you transform and you get the output of the Lth layer, okay, and that is h of x. Okay, so now when you have your data, you have x1, x2, x3 up to xn, and y1, y2, y3 up to yn. Okay, so you can send each data point through your neural network, and you can get h of x1, h of x2, dot 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 dot, h of xn. Okay, and now you've computed the output of your neural network for each input. And what do I need to compute these outputs? I need the weights. So I'm assuming that the weights are given. Okay, so for given weights, W1, W2 up to WL, okay, we can certainly compute the output, okay, which means that we can compute the in-sample error, En of H, which is specified by the weights, is equal to 1 over n. And let me illustrate with the squared error. Sum from I equals, sum from little n equals 1 to big N of h of x little n minus the y value, y little n squared. So this is if we're doing, let's say, regression and we're trying to minimize the squared error. If we were doing classification or logistic regression, we would have different errors. Okay. Actually, classification error is also a squared error, but if we were doing logistic regression, this would be the cross entropy error. So we can, in general, write the in-sample error as the sum 1 over n, the sum over n equals 1 to big N of some error function which takes as it which is computed for h of xn and yn. Okay, and okay, what's the goal now? So this is just saying that if you give me the weights, I can compute my hypothesis outputs for all of my data, and I can compute the in-sample error. Okay, that's nice, but that's not, you know, the main, you know, work that we need to do when we're performing learning. We need to learn. We need to fit these weights now to the data. So in other words, we need to find the weights, okay, that minimize the in-sample error. So we need to fit the neural network, okay, neural network NN to data, i.e. find the weights that minimize the in-sample error. Now, whether or not that's a good thing to do, we'll deal with that later. That's the issue of overfitting. But for the moment, okay, we need to at least be able to fit the data. We need to find the best looking weights. Okay, and, you know, one of the reasons why we put the 10H here is because it's differentiable. We cannot the perceptron on it was already a tough optimization problem. We cannot analytically find these weights, okay? So we need to numerically find these weights, and so we're going to use gradient descent. The algorithm we saw before, this iterative algorithm to minimize a function, okay, which we saw before in the context of logistic regression. Okay? And so the idea here, imagine that, you know, we have the weights, okay? the idea here is to figure out what's the gradient of the in-sample error with respect to your weights, okay, and move and do gradient descent, so take steps in the direction of the negative gradient. So, we're going to update WL, gets updated to WL plus minus your learning rate times the gradient, okay, so the derivative of the in-sample error with respect to your weights WL. So imagine that I want to move let's say I want to move the weight matrices, I want to move the weight matrix W in layer L, okay, in order to improve the in-sample error a little bit. So I figure out the gradient of the in-sample error with respect to the weights WL, and I move a little bit in that negative gradient direction. Okay, and what is the gradient of the in-sample error? Okay, so the gradient of the in-sample error with respect to WL is the gradient of a sum. Okay, so it's 1 over n, the gradient of a sum, but that's a sum of gradients, a sum from n equals 1 to big N, okay, of the gradient of E of h of xn, yn, with respect to dWL. Okay. So we see that we need to be able to take the gradient of this error function with respect to the weights WL. What is the gradient? Effectively, the gradient is saying how much does this error function change if I change the weights? The change in the error function divided by the change in the weights. That's effectively what the gradient is, the derivative. Okay. So, summary. We have a way to compute the output. That's nice, which gives us a way to compute the in-sample error. Okay. And, okay, which is good, but, I can compute the in-sample error for a pre-specified set of weights. Okay, so if you pick random weights, I can compute the in-sample error, but that's not what we want to do when we're doing learning. We want to fit the data. Okay, we want to find the good weights, okay, the weights that minimize the in-sample error. Whether that's a good idea or not is yet to be seen. Okay, and in order to find the good weight, we need to be able to compute the change in the in-sample error or the change in the pointwise error with respect to a change in the weights, okay, in order to run gradient descent. Okay, now in practice, people are using massive networks with, a million parameters and so on and so forth. Okay, so, we have to, at some point, pay a little bit of, attention to practice and efficiency. And we want things to end in a year or in our lifetime. Okay, so quick exercises for you. Okay, so a quick exercise. So we will now, focus a little bit on efficiency as well. So computing the in-sample error. Okay, so if you have n data points, n data points. Okay. And a neural network architecture specified in this way. So imagine that your dimensions of each layer are D0, which is the input dimension, D1, D2, up to D sub L. Okay. So I'll give you a couple of sort of exercises, okay, quizzes. Okay. How many weights are in this network? So, how many weights? I.e., what is the size, the number of entries in W1 plus, plus W2 plus all the way to plus WL. Okay, let's call the number of weights big W. So let's call this W. Okay, size of W. Okay. How many vertices or how many nodes? Let's call that V. How many nodes? Okay. And in order to compute the in-sample error, how many times do you need to compute or evaluate this function theta to compute E in? How many multiplications? So 1 and 2 computations of theta. Okay, so it's very helpful to sort of sit down and answer those pop quizzes. Okay, and I'm going to erase while you answer those pop quizzes. Okay. Okay, so if you did those little pop quizzes, so here's what you should have found. In order to compute h of x, each weight will multiply a corresponding output from a node. So each weight will be touched once for a multiplication. So number of multiplications is equal to the number of weights or number of parameters in your network. So it's equal to the number of weights equals number of parameters. Okay. And the number of times you need to compute this activation function tan h, theta, so the number of computations of theta computations. So you get the signal into the node, you compute theta, and you pass it out, and that's it. You never need to compute theta for that node again. So it's equal to the number of nodes in your neural network, which is which is just the sum of the degrees, basically. It's just the sum of the degrees. Okay, and so in order to compute the in-sample error, okay, we have to compute. So this is to compute h of x. We have to compute h of x n times. So compute E in requires, n times the number of weights, multiplications, plus n times the number of nodes, computations of theta. So this is multiplications, and this is theta computations. Okay, and so, if the theta computation is very costly, then in practice we might choose another activation function, not the tan h. And that's what is the, one of the rationales behind these various, piecewise linear. So 0 up to some threshold and then increasing linear. Okay, so those are much faster to compute. They basically computed using multiplications. Tan h is a relatively expensive, computation.